Right now, as you read this, the Voyager 1 spacecraft is hurtling through interstellar space at 38,000 miles per hour. It's the most distant human-made object ever, over 15 billion miles from Earth. And yet, despite decades of travel, despite leaving our sun's influence behind, Voyager has barely scratched the surface of what we call the solar system. The true edge, the gravitational boundary where the sun's dominance finally ends, lies nearly 1,000 times farther away. That distant frontier, called the Oort Cloud, forms a spherical shell of icy debris stretching halfway to the nearest star. To reach it would take Voyager not decades, but 30,000 years. And that's just to reach the edge of our own cosmic neighborhood. The nearest star beyond our Sun, Proxima Centauri, sits 4.24 light-years away, a distance so vast that our fastest spacecraft would need over 70,000 years to arrive. These aren't just big numbers. They're physical barriers written into the fabric of space itself. Limitations imposed by the universe's most fundamental laws. The dream of interstellar travel, of spreading humanity across the galaxy, crashes headfirst into a wall of physics that no amount of innovation may ever overcome. We are, in the most literal sense, trapped not by technology, but by the architecture of reality itself. The true edge of the solar system. When most people picture the solar system's edge, they imagine Neptune's orbit, or perhaps Pluto, drifting alone in the darkness. But the reality extends far beyond these familiar landmarks. The true boundary of our Sun's gravitational domain reaches almost incomprehensibly farther to a region called the Oort Cloud, a vast spherical shell of frozen comets and debris that marks where our star's influence finally surrenders to interstellar space. This cloud begins roughly 2,000 astronomical units from the Sun, where 1 astronomical unit equals the Earth-Sun distance of 93 million miles, and extends outward to nearly 100,000 astronomical units. To put that in perspective, Neptune orbits at just 30 astronomical units. The Oort Cloud stretches more than 3,000 times farther, forming a bubble nearly 2 light-years across. This makes it the true edge, the final frontier where the Sun's gravity becomes too weak to hold objects in stable orbit. Beyond lies the gravitational territory of other stars, the beginning of true interstellar space. The Oort Cloud itself is a relic of the solar system's formation, a repository of primordial material left over from the swirling disk of gas and dust that birthed our planets 4.6 billion years ago. Gravitational interactions with the giant planets, particularly Jupiter and Saturn, flung countless icy bodies outward during the system's chaotic youth. Some escaped entirely, but many settled into distant, lazy orbits in this outermost zone. Today, the Oort Cloud contains trillions of objects, most no larger than mountains, composed primarily of water ice, methane, and ammonia. Occasionally, a passing star's gravity nudges one of these frozen wanderers inward, sending it on a million-year journey toward the inner solar system, where it becomes a long-period comet. Those spectacular visitors, with orbits lasting thousands of years. We've never directly observed the Oort Cloud because its objects are too small and too far away to reflect enough sunlight for our telescopes to detect. Its existence is inferred from the orbits of long-period comets, which arrive from random directions rather than following the plane of the planets. Their trajectories trace back to this distant reservoir, confirming its presence through mathematics rather than direct observation. The sheer scale of the Oort Cloud redefines what we mean by leaving the solar system. When Voyager 1 crossed the heliopause in 2012, the boundary where the solar wind gives way to interstellar medium headlines proclaimed it had left the solar system. But gravitationally speaking, Voyager remains firmly within the Sun's domain. It won't reach the inner edge of the Oort Cloud for another 300 years, and won't emerge from the outer edge for nearly 30,000 years. Even at its current speed of 38,000 miles per hour, the spacecraft crawls through space on what is, cosmically speaking, an endless journey. This vast region also serves as the true test of any interstellar mission. A spacecraft attempting to reach another star must first traverse this enormous shell of debris, maintaining power and navigation for tens of thousands of years before even approaching the halfway point to Proxima Centauri. The Oort Cloud is not just distant, it's a temporal barrier, a span of time so long that it exceeds all of recorded human history many times over. Engineering a probe to survive such a journey presents challenges beyond our current capabilities. Temperature regulation, power generation, navigation, and communication all become exponentially more difficult as distance increases. The sun's light, which provides both energy and a point of reference, dims to just another star in the sky. Cosmic radiation, unshielded by any planetary magnetosphere or solar wind, bombards the spacecraft continuously. Micrometeorite impacts, though rare, become statistically inevitable over such timescales. Even the materials themselves, the metal, circuitry, and structural components face slow degradation from radiation exposure and thermal cycling. The Oort Cloud also illustrates a fundamental problem with interstellar travel. Distance scales in space don't match human intuition. We're accustomed to thinking of space as empty, but this emptiness is so vast that even light, traveling at 186,282 miles per second, takes nearly 2 years to cross from one side of the Oort Cloud to the other. For any physical spacecraft limited by the laws of physics as we understand them, this region represents not just a boundary, but a seemingly insurmountable gulf between our home system and the rest of the galaxy. The tyranny of the rocket equation. Every spacecraft ever launched, from the first Sputnik satellite to the most advanced interplanetary probe, operates under the iron law of the rocket equation, a mathematical relationship that governs how much fuel is needed to achieve a given change in velocity. First formulated by Russian scientist Konstantin Tsiolkovsky in 1897, this equation reveals a brutal truth. The faster you want to go, the exponentially more fuel you need to carry. And the more fuel you carry, the heavier your spacecraft becomes, requiring even more fuel to accelerate that additional mass. This vicious cycle creates a fundamental barrier to high-speed space travel. The rocket equation states that the change in velocity a spacecraft can achieve is proportional to the exhaust velocity of its propellant multiplied by the natural logarithm of the ratio between its initial mass, including fuel, and its final mass after fuel is burned. In practical terms, this means that to double your speed, you don't need twice as much fuel, you need exponentially more. Chemical rockets, which power all current launch vehicles, achieve exhaust velocities of roughly 4,500 meters per second. To reach even 1% of light speed, about 3,000 kilometers per second, using conventional chemical propulsion would require a fuel-to-payload mass ratio so enormous that it becomes physically impossible. You would need more fuel than exists in the observable universe to accelerate even a small probe to a meaningful fraction of light speed. The numbers become absurd. A 1-ton spacecraft attempting to reach 10% light speed with chemical rockets would need a fuel tank weighing more than 10 to the power of 34 kilograms, billions of times the mass of the entire solar system. Even nuclear propulsion, which offers exhaust velocities 10 times higher than chemical rockets, runs into the same exponential wall. Project Orion, a 1,960 concept that proposed using nuclear bomb detonations to propel a spacecraft, could theoretically achieve velocities of 30,000 kilometers per second, about 10% of light speed. But the engineering challenges proved insurmountable. The spacecraft would need to carry thousands of nuclear devices, each detonating behind a massive shock absorber called a pusher plate. The radiation exposure, the mechanical stress, and the sheer logistics of such a system pushed it beyond feasibility. Modern concepts like ion drives and plasma engines offer higher exhaust velocities by using electric or magnetic fields to accelerate charged particles. NASA's Dawn spacecraft used ion propulsion to explore the asteroid belt, achieving exhaust velocities of 30,000 meters per second. But ion drives produce minuscule thrust measured in fractions of a newton, comparable to the weight of a sheet of paper pressing on your hand. They can accelerate continuously for years. But even with this sustained thrust, reaching interstellar velocities requires massive power sources and decades of acceleration. To escape the rocket equation's tyranny, some proposals suggest not carrying fuel at all. Solar sails use pressure from sunlight to accelerate, requiring no propellant. The Breakthrough Starshot initiative plans to use powerful ground-based lasers to push lightweight probes equipped with reflective sails, potentially accelerating them to 20% of light speed. But even this approach faces enormous obstacles. The laser array would need to be hundreds of square kilometers in size, consuming gigawatts of power, and the probe would need to be incredibly small, just grams in mass, to achieve meaningful acceleration. Such a craft couldn't carry significant instruments, communication equipment, or shielding, limiting its scientific utility. The problem compounds when we consider not just reaching another star, but slowing down upon arrival. The rocket equation applies equally to deceleration. A probe traveling at 10% light speed carries enormous kinetic energy. Hitting interstellar gas and dust at such velocities would generate intense heating and radiation. To decelerate using conventional propulsion, you'd need to carry fuel for the braking burn, which means carrying even more fuel for the initial acceleration to compensate for that additional mass. The mass ratios spiral into impossibility. Some concepts propose using magnetic sails or drag devices to slow down using the interstellar medium itself, but at relativistic speeds, even the tenuous gas between stars would create significant resistance and radiation exposure. Relativistic energy requirements. As spacecraft approach significant fractions of light speed, the energy requirements don't just increase, they explode according to Einstein's theory of special relativity. This isn't a limitation of current technology. It's a fundamental property of the universe. The faster an object moves, the more its relativistic mass increases, requiring exponentially more energy to accelerate further. At low speeds, this effect is negligible, but as you approach light speed, it becomes the dominant factor, creating an insurmountable energy barrier. Consider a 1-ton spacecraft, roughly the mass of a small car. To accelerate it to just 10% of light speed requires approximately 4.5 times 10 to the power of 17 joules of energy, equivalent to the total energy output of a large nuclear power plant running continuously for several years. But the energy doesn't scale linearly. To reach 50% of light speed, that same spacecraft would require not 5 times the energy, but roughly 15 times as much, about 7 times 10 to the power of 18 joules. At 90% of light speed, the energy requirement balloons to 1.2 times 10 to the power of 20 joules, more than 250 times the energy needed for 10% light speed. And these calculations assume perfect efficiency, that every joule of input energy translates directly into kinetic energy with no losses to heat, radiation, or mechanical inefficiency. In reality, no propulsion system approaches perfect efficiency. Chemical rockets convert only about 60% of fuel energy into thrust. Nuclear systems might reach 80%. Even theoretical fusion drives, which could convert matter to energy with unprecedented efficiency, would still lose significant energy to waste heat and radiation. The relativistic energy barrier also means that even if we could somehow generate the required power, delivering it to the spacecraft becomes problematic. Solar panels can't provide enough energy at interstellar distances. Nuclear reactors, while energy-dense, add significant mass that must also be accelerated. Antimatter, which offers the highest energy-to-mass ratio possible, is phenomenally expensive to produce and dangerous to store. Current production rates measure in nanograms per year, while a useful antimatter fuel supply would require kilograms or tons. The situation worsens when we consider that relativistic speeds turn even tiny particles into devastating projectiles. At 90% of light speed, a single hydrogen atom, the most common element in interstellar space, carries the kinetic energy of a rifle bullet. A grain of sand becomes equivalent to a hand grenade. The interstellar medium, far from being empty, contains roughly 1 atom per cubic centimeter. A spacecraft traveling at relativistic speeds would encounter billions of such atoms every second, each impact generating heat and radiation. Shielding against this bombardment would require massive armor, adding weight that must be accelerated to those same extreme velocities. The energy cost spirals upward. Some theoretical designs propose using the shield material as reaction mass, essentially ablating away as it absorbs impacts, but this requires carrying even more mass initially. Moreover, Einstein's equations tell us that as an object approaches light speed, time itself dilates, slows down relative to stationary observers. While this could theoretically allow crew members to experience shorter journey times, it doesn't reduce the energy required. In fact, it creates additional problems. A crew experiencing months while decades or centuries pass on Earth would face massive synchronization issues, including the possibility that Earth's civilization might have changed or disappeared entirely by the time they arrive. The Lorentz factor, which quantifies these relativistic effects, approaches infinity as velocity approaches light speed, meaning no amount of energy can accelerate a massive object to exactly light speed, the cosmic speed limit. The speed of light, precisely 299,792,458 meters per second, isn't just the universe's speed limit. It's an absolute barrier woven into the fundamental structure of spacetime itself. Einstein's special relativity demonstrates that this limit isn't a technological hurdle waiting to be overcome, but rather a consequence of how space and time are unified into a single four-dimensional continuum. Nothing with mass can reach light speed, and this prohibition has profound implications for interstellar travel. Light itself travels at this ultimate speed because photons have no rest mass. For any object with mass, even something as small as an electron, reaching light speed would require infinite energy. The mathematics is unambiguous. As velocity increases, relativistic mass increases, requiring more and more energy to produce smaller and smaller increments of additional speed. The curve approaches but never reaches light speed, creating an asymptote that represents an impenetrable ceiling. Even if we could somehow generate unlimited energy, the universe's structure prevents us from using it to achieve light speed. This speed limit also dictates the minimum travel time to any destination. Proxima Centauri, our nearest stellar neighbor at 4.24 light-years, would require at least 4.24 years to reach, even if we could somehow travel at light speed itself. The galactic center lies 26,000 light-years away, a minimum 26,000-year journey. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years distant. Even a signal traveling at light speed takes this long to cross such distances, meaning real-time communication with any craft becomes impossible beyond our immediate neighborhood. The speed of light also imposes severe restrictions on navigation and collision avoidance. A spacecraft traveling at even 10% of light speed covers about 30,000 kilometers per second. At such velocities, detecting and avoiding obstacles becomes nearly impossible. Light from an approaching object takes time to reach the spacecraft, but by the time sensors register a threat, the object may be only seconds away. Reaction time for course corrections shrinks to virtually nothing. Autonomous navigation systems would need to operate on timescales faster than human reflexes, making decisions based on incomplete information about the space ahead. The universe's expansion, driven by dark energy, adds another layer to this speed limit. Distant galaxies recede from us faster than light, not because they're moving through space faster than light, but because space itself expands between us. This means that regions of the universe beyond a certain distance, called the cosmic horizon, are forever unreachable. No matter how fast we travel, we can never reach galaxies that are currently receding faster than light, because the space between us grows faster than we can traverse it. The observable universe has a radius of about 46 billion light-years, but the reachable universe, the region we could potentially visit, is far smaller and shrinking. Some physicists have proposed theoretical workarounds to the light speed barrier, but all face insurmountable obstacles. Wormholes, hypothetical tunnels through space-time connecting distant points, would require exotic matter with negative energy density, something never observed and possibly forbidden by quantum mechanics. The Alcubierre drive concept suggests contracting space in front of a spacecraft while expanding it behind, essentially moving space itself rather than moving through space. But this would require amounts of negative energy equivalent to the mass energy of entire planets, and possibly violate causality itself by creating closed time-like curves, paths through spacetime that loop back to earlier moments, potentially allowing time travel paradoxes. Quantum entanglement, which Einstein called spooky action at a distance, allows correlated particles to instantaneously affect each other, regardless of separation. But this phenomenon cannot transmit information faster than light. When one entangled particle is measured, its partner's state becomes determined. But this correlation can only be verified by comparing measurements through conventional, slower-than-light communication. No violation of causality occurs, and no useful information can be transmitted faster than light. The speed limit isn't arbitrary, it emerges from the geometry of spacetime itself, time dilation and the generation problem. Even if we could approach significant fractions of light speed, Einstein's relativity introduces another profound barrier: time dilation, the phenomenon where time passes more slowly for objects moving at relativistic velocities compared to stationary observers. This isn't science fiction, it's been confirmed countless times through experiments with atomic clocks on aircraft and satellites. For interstellar travel, time dilation creates an irreconcilable split between the experience of the travelers and everyone left behind, making conventional space travel a one-way journey into the future. The mathematics of time dilation follow from the Lorentz transformation. At 90% of light speed, time aboard a spacecraft passes at roughly 44% the rate of time on Earth. A journey to a star 10 light-years away would take about 11 years from Earth's perspective, but only about 4.8 years for the crew. This sounds advantageous, the crew ages less, but it creates insurmountable problems for any civilization attempting systematic exploration or colonization. Consider a mission to Proxima Centauri at 80% of light speed. Earth-based observers would measure the journey time at about 3 years each way. The crew, experiencing time dilation, would age only about 3.2 years during transit. But when they arrive and send signals back to Earth, those signals take 4.24 years to arrive. By the time Earth receives confirmation of their arrival, nearly a decade has passed. Any response takes another 4.24 years to reach the spacecraft. The conversation lag makes real-time support impossible. If problems arise, the crew must solve them with resources on hand. No one can send help. For longer journeys, the temporal disconnect becomes absurd. A round trip to a star, 1,000 light-years away, at 99.99% of light speed, might take only about 28 years from the crew's perspective, but 2,000 years would pass on Earth. The travelers would return to a world transformed beyond recognition. Cultures changed, languages evolved, possibly entire civilizations risen and fallen. Everyone they knew would be dead for centuries. Technology would have advanced so dramatically that the returning spacecraft might seem like an ancient relic. This creates what's called the generation problem, though it manifests differently than in slower-than-light travel. For sublight journeys taking centuries or millennia from both perspectives, the traditional generation problem involves maintaining a viable population across dozens or hundreds of generations aboard a vessel. These generation ships would face genetic bottlenecks, social instability, technological decay, and the psychological challenges of raising generation after generation, knowing they'll never see the destination. But time dilation doesn't solve this, it trades one problem for another. High-speed travelers experience shorter journeys, but become temporal exiles, disconnected from their home civilization. This temporal exile has practical implications for mission planning. Space agencies can't maintain institutional knowledge or support infrastructure for millennia. Private ventures can't expect return on investment across such timescales. Even if suspended animation or hibernation technology became available, freezing crew members for the journey, it doesn't solve the communication problem or the fact that mission control will be gone before the mission concludes. The ship becomes utterly autonomous, carrying not just people, but an entire self-sufficient civilization capable of operating independently for its entire journey. Another complication: relativistic travel requires enormous initial energy expenditure, but decelerating at the destination requires equal energy. A spacecraft can't carry enough fuel for both acceleration and deceleration, plus the fuel needed to accelerate that deceleration fuel. Alternative schemes propose using magnetic sails to brake against the interstellar medium or aimed lasers from the destination to push against solar sails during approach. But these require infrastructure at the destination infrastructure that doesn't exist and can't be built without first sending an expedition, creating a circular problem. Even communication becomes strange under time dilation. Radiation in deep space. Beyond the protective bubble of Earth's magnetosphere and the heliosphere, the vast magnetic field generated by our sun space becomes a shooting gallery of deadly radiation. This isn't the gentle warmth of sunlight filtered through an atmosphere, but high-energy particles and electromagnetic radiation capable of shredding DNA, damaging electronics, and slowly poisoning any living thing exposed to it. For interstellar travel, radiation exposure isn't just a health hazard, it's a fundamental barrier that grows more severe with journey duration and distance. The radiation environment of deep space consists of three primary threats. First, galactic cosmic rays, high-energy particles, mostly protons and atomic nuclei, accelerated to near-light speeds by supernova explosions and other violent cosmic events. These particles carry enormous energy, enough to punch through spacecraft hulls, shielding, and human tissue. They're omnidirectional, arriving from all angles simultaneously. And unlike solar radiation, they can't be blocked by simply positioning a shield in one direction. Second, solar energetic particles, bursts of radiation from solar flares and coronal mass ejections. Though the heliosphere partially shields against these near-Earth, beyond the heliopause their source becomes irrelevant as galactic cosmic rays dominate. Third, secondary radiation is created when primary particles strike spacecraft materials. When a high-energy cosmic ray hits the hull of a ship, it doesn't simply stop, it fragments atomic nuclei in the material, creating a cascade of secondary particles including neutrons, gamma rays, and charged particles that scatter in multiple directions. This shower of secondary radiation can be more dangerous than the initial impact. Astronauts on the International Space Station, protected by Earth's magnetosphere, receive radiation doses of about 150 millisieverts per year, roughly 50 times the dose a person on Earth's surface receives. This is considered acceptable for short-duration missions. But on a journey to Mars, outside the magnetosphere for months, astronauts would accumulate doses of 500 to 700 millisieverts. NASA's career limit for astronauts is 1,000 millisieverts, which corresponds to a 3% increase in lifetime cancer risk. On an interstellar journey, with no planetary magnetic field and no solar wind to provide even minimal shielding, radiation doses would be orders of magnitude higher. Traditional shielding approaches adding thick layers of aluminum or lead don't work well against cosmic rays. Dense materials can actually make the problem worse by generating more secondary particles. Research shows that lighter elements like hydrogen, which can't fragment much when struck because they're already the simplest atoms, provide better protection per unit mass. Water, polyethylene, and liquid hydrogen have been proposed as shielding materials. But effective radiation shielding requires massive amounts of material, several meters thick, which adds enormous mass to the spacecraft. Every kilogram of shielding must be accelerated along with the rest of the vehicle, multiplying fuel requirements and making the rocket equation even more punishing. Some designs propose surrounding living quarters with water tanks or fuel storage, using necessary consumables as dual-purpose radiation shields. But this only works while those reserves last. As water is used and fuel burned, protection degrades. Other concepts involve active shielding, using powerful magnetic fields to deflect charged particles, mimicking Earth's magnetosphere. The challenge is generating fields strong enough to bend the trajectories of cosmic rays before they penetrate the ship. This requires superconducting magnets, consuming significant power and adding substantial mass. Prototype systems tested on Earth show promise, but remain far from practical implementation for spacecraft. The biological effects of prolonged cosmic ray exposure extend beyond cancer. High-energy particles damage the central nervous system, potentially causing cognitive impairment, memory loss, and behavioral changes effects observed in animal studies, but difficult to quantify for humans on multi-year journeys. Radiation also increases the risk of cataracts, cardiovascular disease, and degenerative tissue damage. These aren't minor inconveniences but mission-critical concerns. A crew suffering cognitive decline might become unable to operate complex systems or respond to emergencies. Radiation doesn't just threaten organic life, it degrades spacecraft, electronics, and materials. Cosmic rays can trigger single-event upsets in computer memory, flipping bits and corrupting data. They can damage solar panels, reducing power generation efficiency over time. Structural materials become brittle as their atomic structure is disrupted by particle impacts. Polymer seals and insulation degrade under radiation exposure. Over decades or centuries, these effects accumulate, requiring either massive redundancy in all systems or periodic replacement of components difficult or impossible on an interstellar voyage with no possibility of resupply. The interstellar medium barrier. Space between stars is often described as empty, a vacuum more perfect than anything achievable in laboratory conditions on Earth. But this description is misleading. The interstellar medium, the gas and dust scattered thinly between star systems, contains approximately 1 atom per cubic centimeter, mostly hydrogen with traces of helium and heavier elements. At everyday speeds, this tenuous material poses no threat. But at relativistic velocities, even this near vacuum becomes a devastating obstacle, transforming individual atoms into high-energy projectiles capable of eroding spacecraft and generating lethal radiation. The physics is straightforward. Kinetic energy increases with the square of velocity. At 10% of light speed, about 30,000 kilometers per second, a single hydrogen atom carries the kinetic energy of a grain of sand dropped from shoulder height. Harmless on Earth, but a spacecraft traveling this fast encounters billions of such atoms every second. Each impact transfers energy into the spacecraft's hull as heat and structural stress. At 90% of light speed, each hydrogen atom hits with the energy of a bullet fired from a rifle. The interstellar medium becomes, in effect, a continuous sandblasting barrage. The damage mechanisms are complex. Direct erosion gradually ablates material from the spacecraft's leading surfaces, thinning the hull and degrading structural integrity. This process is slow but relentless over years or decades of travel. Even thick armor wears away. More immediately dangerous is the radiation generated by these impacts. When high-velocity atoms collide with spacecraft materials, they trigger nuclear reactions in the target nuclei, creating cascades of secondary particles, including neutrons, gamma rays, and charged fragments. This secondary radiation penetrates deep into the spacecraft, irradiating electronics, structural components, and, if present, biological tissue. The faster the spacecraft travels, the more energetic these collisions become, and the more intense the radiation generated. Engineering solutions face severe constraints. Adding frontal shielding protects against erosion, but adds mass that must be accelerated, worsening the rocket equation problem. Thick shields also generate more secondary radiation when struck, potentially making the problem worse. Some proposals suggest using electromagnetic fields to ionize and deflect incoming atoms before they hit the hull. But at relativistic speeds, the deflection distance shrinks. Particles move too fast for even powerful magnetic fields to bend their trajectories significantly. The field would need to extend hundreds or thousands of kilometers ahead of the spacecraft to provide adequate deflection distance, requiring magnetic field strengths far beyond current technology. Another approach proposes a sacrificial shield, a dense cloud of particles, or a thin solid barrier positioned ahead of the spacecraft. Incoming atoms collide with this shield instead of the ship itself, but the shield must be continuously replenished as it erodes, requiring enormous reserves of material. Alternatively, a solid shield could be deployed on a tether, positioned kilometers ahead of the main craft. But at relativistic speeds, even a small shield must withstand tremendous forces. The structural tether connecting it to the spacecraft would need to be incredibly strong to resist being torn apart by the constant bombardment. Dust grains pose an even greater threat than individual atoms. Interstellar space contains microscopic dust particles, typically silicates, and carbon compounds at densities of roughly 1 grain per several cubic kilometers. These particles range from nanometers to micrometers in size. At relativistic speeds, a dust grain the size of a bacterium carries as much kinetic energy as a hand grenade. A particle the size of a sand grain hits with the force of a large bomb. Even a single such impact could catastrophically damage or destroy a spacecraft traveling at 90% of light speed. The communication problem. Even if we solved every other challenge and launched a successful interstellar mission, communication with that spacecraft presents problems that fundamentally limit the mission's utility. The speed of light, which constrains travel velocity, also limits information transfer. Signals from a probe at Proxima Centauri take 4.24 years to reach Earth, creating conversation lags measured in years or decades. For more distant destinations, the lag extends to centuries or millennia, making real-time mission control impossible and reducing interstellar exploration to launching probes into darkness with minimal hope of useful feedback. Consider a spacecraft approaching Alpha Centauri. When mission engineers on Earth see telemetry indicating a problem, the data is already years old. By the time they analyze the situation, formulate a solution, and transmit instructions back, the spacecraft has been dealing with the problem for 8 years, or the problem has already destroyed the probe. Autonomous systems must handle all emergencies without human intervention, requiring artificial intelligence far more sophisticated than current technology, capable of diagnosing novel problems and improvising repairs with available resources. The inverse square law compounds this difficulty. Radio signals spread out as they travel, weakening with the square of the distance. A signal broadcast from Earth reaches Mars, diminished by a factor of roughly 100 compared to its transmission strength. At Proxima Centauri, that same signal is trillions of times weaker. Detecting such faint transmissions requires enormous antennas and receivers. NASA's Deep Space Network, used to communicate with Voyager spacecraft at the edge of the solar system, employs 70-meter radio dishes and can barely maintain contact at current Voyager distances. For interstellar communication, we'd need antenna arrays hundreds or thousands of meters across, consuming enormous power to generate detectable signals and extraordinary sensitivity to receive faint replies. The spacecraft faces even greater challenges. It can't carry a 70-meter dish mass. Constraints demand much smaller antennas, and power is severely limited. Solar panels become useless in deep space, where sunlight is negligible. Nuclear reactors can provide power, but they're heavy, and their fuel eventually depletes. Radioisotope thermoelectric generators, used on Voyager and other deep space probes, generate only hundreds of watts and decay over decades. Broadcasting a signal strong enough to reach Earth across light years requires kilowatts or megawatts of power, far beyond available sources for a small spacecraft. Focusing the signal helps. A narrow beam transmission wastes less power by concentrating energy in the direction of Earth, rather than broadcasting in all directions. But this requires extremely precise pointing. At interstellar distances, an error of even a fraction of a degree causes the beam to miss Earth entirely. The spacecraft must know Earth's exact position, which changes as our planet orbits the Sun, and maintain precise attitude control for years or decades. Any tumbling or drift caused by micrometeorite impacts, outgassing, or mechanical failures could permanently break the communication link. Data rate presents another limitation. The farther the signal travels and the weaker it becomes, the slower the data must be transmitted to ensure accuracy. Deep space missions to the outer solar system manage data rates, measured in bits per second, barely enough for low-resolution images and basic telemetry. Interstellar distances would reduce rates further, possibly to fractions of a bit per second. Downloading a single high-resolution image could take months or years. A comprehensive scientific dataset from an exoplanet atmospheric spectra, surface mapping, compositional analysis might require decades or centuries to transmit. The problem worsens for crewed missions. Psychological health requires regular communication with Earth, but delays make conversation impossible. A question sent to Earth receives no answer for years. By the time a reply arrives, the original context may be irrelevant. Crew members become isolated in time as well as space, unable to participate in Earth's cultural or scientific developments. Relationships with loved ones decay into slow-motion monologues. Emergency medical consultations become impossible. Doctors light years away can't provide timely advice for acute conditions. Interstellar networks have been proposed to address these issues. Relay stations positioned at intervals between stars to amplify and forward signals, reducing total distance any single transmission must travel. But building such infrastructure requires deploying stations across light years of space, each needing its own power source, communication equipment, and autonomous maintenance systems. The cost and complexity would be staggering, and the entire network would take centuries to establish, even if we could launch the necessary hardware. Some concepts propose using laser communication instead of radio. Lasers can be focused more tightly, concentrating energy into narrow beams that spread less over distance. But laser systems face their own problems. They require even more precise pointing than radio antennas, and interstellar dust and gas scatter and absorb laser light, reducing signal strength. Atmospheric absorption on Earth limits which wavelengths can penetrate to ground-based receivers, necessitating space-based receiving stations. Power generation across the void. Every spacecraft requires power for propulsion, life support, communication, navigation, and scientific instruments. Near Earth, solar panels provide abundant energy, converting sunlight into electricity with reasonable efficiency. But beyond Mars, sunlight weakens rapidly. At Jupiter's distance, solar intensity drops to about 4% of Earth's level. At Neptune, it's less than 0.1%. In interstellar space, the Sun becomes just another star, barely brighter than others, visible in the night sky, making solar power essentially useless. Missions venturing into the outer solar system and beyond must carry their own power sources, but every option faces severe limitations that worsen with mission duration and distance. Radioisotope thermoelectric generators, or RTGs, power most deep space missions including Voyager, Cassini, and Curiosity. These devices use the heat from radioactive decay, typically plutonium-238, to generate electricity through thermoelectric converters. RTGs are reliable, have no moving parts, and operate continuously for decades. Voyager's RTGs, launched in 1977, still function today, nearly 50 years later, though their power output has declined significantly. RTGs generate only a few hundred watts initially, and their output decreases as the radioactive material decays. Plutonium-238 has a half-life of 88 years, meaning power drops by half roughly every 9 decades. A mission lasting thousands of years necessary for interstellar travel would see power output drop to negligible levels long before reaching its destination. Global production measures in kilograms per year, while a large interstellar spacecraft would require hundreds of kilograms or tons to generate meaningful power. Nuclear fission reactors offer higher power output. Space reactor concepts like SNAP-10A, tested briefly in the 1960s, or more modern designs like kilopower, can generate kilowatts or even megawatts of electricity. They operate by sustaining a controlled nuclear chain reaction, using the heat to drive turbines or thermoelectric converters. Fission reactors are compact relative to their power output and can theoretically operate for years or decades before fuel depletion. But they add significant mass reactor cores, shielding, cooling systems, and fuel all contribute weight that must be accelerated along with the spacecraft. They also require cooling, which in space means large radiators to dissipate waste heat. At steady-state operation, a reactor might reject several megawatts of thermal energy, necessitating radiator panels covering hundreds of square meters. These panels are vulnerable to micrometeorite impacts and add drag if any residual gas is present. Nuclear fusion, the process powering stars, offers even greater energy density than fission. Fusion reactors would combine light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, releasing enormous energy. Fusion produces more energy per unit mass than any other known process, except matter, antimatter, annihilation, and fusion fuel is far easier to obtain than antimatter. But despite decades of research and billions in funding, sustained controlled fusion for power generation remains unachieved on Earth. Experimental reactors like ITER aim to demonstrate net energy production, but won't be operational until the 2030 at earliest. And scaling such technology to spacecraft dimensions introduces additional challenges. Antimatter represents the ultimate energy source, converting mass directly to energy with 100% efficiency, according to Einstein's equation, E equals mc squared. Just grams of antimatter could power a spacecraft for years, but antimatter doesn't exist naturally in usable quantities, and must be manufactured in particle accelerators at enormous expense. Current production costs billions of dollars per milligram. Storage is another nightmare. Antimatter annihilates instantly upon contact with normal matter, requiring magnetic confinement systems that themselves consume power and add mass. Producing enough antimatter to fuel an interstellar mission would require centuries at current production rates and energy expenditures exceeding entire nations' power grids. Another fundamental constraint is waste heat. All power generation produces waste heat. Even perfectly efficient systems converting mass to energy must radiate the energy they don't use. In space, the only way to shed heat is through radiation, which becomes less efficient as radiators cool. High-power systems require enormous radiator surface areas, adding mass and creating fragile structures vulnerable to damage. At relativistic speeds, impacts with interstellar gas and dust heat the spacecraft continuously, compounding the thermal management problem. The ship must radiate not only waste heat from its power systems, but also the kinetic heating from continuous particle bombardment. Navigation without landmarks. On Earth, navigation seems straightforward. We have maps, GPS satellites, compasses, and visible landmarks. Even ocean vessels, far from shore, navigate using stars, compasses, and now satellite positioning systems. But in interstellar space, traditional navigation techniques fail. There are no landmarks, no fixed reference points, no GPS constellation. Stars themselves move, and their apparent positions shift with parallax as the spacecraft travels. Determining position and velocity with sufficient accuracy to reach a target light years away, and maintaining that accuracy across decades or centuries, presents challenges that grow exponentially with distance. The fundamental problem is that space is vast and mostly featureless. Near Earth, spacecraft use ground-based tracking radio signals sent from Earth and bounced back by the craft, allow precise measurement of distance and velocity using signal delay and Doppler shift. But this technique's accuracy degrades with distance. At interstellar ranges, even tiny uncertainties in position and velocity measurements accumulate into enormous errors. A velocity error of just 1 meter per second, a walking pace, compounds over a 10-year journey into a positional error of 300 million kilometers, more than the distance from Earth to Mars. Miss your target by that much, and you fly past your destination star system without slowing down. Inertial navigation, used by submarines and aircraft, tracks position by integrating acceleration measurements over time, using gyroscopes and accelerometers. But this method suffers from drift. Small errors in sensor readings accumulate continuously, causing calculated position to diverge from true position. Even the best inertial navigation systems drift by kilometers per hour. Over years or decades, this drift renders dead reckoning useless without periodic corrections. Stellar navigation, using the positions of stars as references, works well for determining orientation but struggles with position. Stars are so distant that they appear fixed from any position within our solar system. Only when traveling substantial fractions of a light year does parallax, the apparent shift in star positions due to the observer's motion, become detectable. Measuring this parallax requires extremely precise angle measurements, far beyond current sensor capabilities. And even with perfect measurements, calculating position requires knowing the exact three-dimensional coordinates of reference stars' data we don't have with sufficient precision for most stars. Pulsars offer a potential solution. These rapidly rotating neutron stars emit radio pulses with extremely stable periods, acting like cosmic lighthouses. Their pulse arrival times can be measured with high precision, and since pulsars are distributed throughout the galaxy, a spacecraft could triangulate its position by measuring signals from multiple pulsars simultaneously. This technique, called pulsar timing navigation, was demonstrated on NASA's NICER experiment aboard the International Space Station. But it requires large, sensitive radio antennas to detect faint pulsar signals and considerable computing power to process the data. For a small, power-limited interstellar probe, this may be impractical. Course corrections add another layer of complexity. Suppose navigation sensors detect that the spacecraft is drifting off course. Correcting the trajectory requires firing thrusters, which consumes fuel that must be carried from the start, worsening the rocket equation problem. The farther the spacecraft has traveled before detecting the error, the more fuel is needed to correct it. A large error discovered late in the journey might require more fuel than the spacecraft carries, rendering the mission a failure. Optimal navigation demands frequent, small corrections rather than rare, large ones, but each correction burns fuel and depletes limited reserves. Gravitational influences complicate navigation further. Stars don't sit motionless in space, they orbit the galactic center at hundreds of kilometers per second, and nearby stars can perturb each other's motion. A target star's position when the spacecraft launches won't be its position when the craft arrives decades later. Calculating the intercept course requires modeling the star's motion accurately, accounting for gravitational influences from nearby stellar companions, dark matter distribution, and the galaxy's overall gravitational field. Small errors in these models translate to large positional errors at journey's end. Relativistic effects introduce additional complications. At significant fractions of light speed, time dilation and length contraction alter the spacecraft's reference frame relative to the target star. Navigation calculations must account for relativistic corrections, which become non-negligible above 10% of light speed. The spacecraft's clocks run slower than Earth's, and distances along the direction of motion appear contracted. These effects must be factored into trajectory calculations. Failure to do so would cause the craft to miss its target. Even defining position becomes ambiguous at relativistic speeds due to the relativity of simultaneity. The psychological abyss. Human psychology evolved for life on Earth. Solid ground beneath our feet, open skies above, a 24-hour day-night cycle, and the presence of complex ecosystems. Spaceflight contradicts all of these conditions. Astronauts on the International Space Station orbiting just 400 kilometers above Earth with constant view of our planet and regular communication with mission control, still report psychological stress, isolation, and sensory monotony. Extending human presence to interstellar distances where Earth becomes invisible, where communication delays measure in years, and where journeys last decades or centuries pushes human psychology into entirely uncharted territory, with risks we can barely anticipate. The phenomenon known as the overview effect, the cognitive shift astronauts experience when viewing Earth from space, demonstrates how profoundly space alters human consciousness. Seeing our planet as a fragile sphere against the void triggers existential reflection and often lasting psychological change. But on an interstellar voyage, even this view disappears. Earth would shrink to a pale dot, eventually indistinguishable from other stars, leaving crew members in complete isolation from everything familiar. The psychological impact of such disconnection is unknown, because no human has ever experienced it, but evidence from extreme isolation studies on Earth, Antarctic winter over cruise, submarine deployments, long-duration cave expeditions shows that humans struggle with confinement, monotony, and separation from natural environments. Astronauts aboard the ISS experience confinement in a space roughly equivalent to a 6-bedroom house, shared with a handful of crew members for missions lasting up to a year. They report cabin fever, interpersonal conflicts, sleep disruption, and difficulty concentrating despite carefully designed living spaces and frequent resupply missions. An interstellar spacecraft would offer even less space per person, shared for far longer periods with no possibility of early return or outside help. Boredom, routine, and the absence of natural stimuli grind down psychological resilience. Earth's environment provides constant, subtle variation, weather changes, seasonal shifts, diverse sensory inputs from ecosystems. Spacecraft offer none of this. Every day is identical to the last. Same walls, same people, same tasks, same recycled air, and artificial light. Studies show that sensory deprivation and environmental monotony lead to depression, cognitive decline, and impaired decision-making. The problem worsens over time as the human brain's need for novelty goes unsatisfied. Interpersonal dynamics become critical and fragile. Crew selection for long-duration missions must account not just for technical skills, but for psychological compatibility. Even carefully selected, compatible individuals develop conflicts under stress. Small irritations magnify into serious disputes when there's no escape, no privacy, no way to avoid someone you've come to dislike. Historical examples from isolated research stations and submarine crews document relationship breakdowns, factionalism, and even violence when groups are confined too long in stressful environments. On an interstellar ship, with no possibility of extraction or crew rotation, such conflicts could become mission-threatening. Cultural and social isolation adds another dimension. Crew members would lose connection with Earth's evolving culture, language, technology, and social norms. Time dilation, if relativistic speeds are achieved, would worsen this. Crew might experience only a decade of subjective time, while centuries pass on Earth. Returning or even communicating would be like stepping into an alien civilization. The knowledge that everyone they knew is dead, that their cultural context has disappeared, creates a form of existential homesickness with no remedy. Even without relativistic travel, the sheer duration of interstellar journeys means mission designers must consider multi-generational crews, children born in space, who will live and die without ever setting foot on a planet. Raising children in such an environment presents staggering challenges. They would lack exposure to Earth's ecosystems, biodiversity, and natural environments, elements that may be essential for healthy psychological development. They would grow up in a closed, artificial world where every resource is rationed and every person's role predetermined by mission needs. The psychological toll of being born into a purpose you didn't choose, in a place you can't leave, traveling toward a destination you'll never see, could be devastating. Maintaining motivation across generations also becomes problematic. The original crew volunteers for the mission understands its purpose and accepts the sacrifice, but their children and their children's children may resent the isolation and constraints imposed on them by ancestors' decisions. Multi-generational missions risk social breakdown as later generations question the mission's purpose or refuse to continue it. The engineering impossibility of generation ships. If interstellar travel requires centuries or millennia, one frequently proposed solution is the generation ship, a massive, self-contained spacecraft designed to house a viable population across multiple generations, essentially a flying world capable of supporting human life for hundreds or thousands of years. The concept appears in countless science fiction stories, but engineering analysis reveals challenges so profound that generation ships may be practically impossible to build and operate. Start with the most basic requirement: size. A viable breeding population requires genetic diversity to avoid inbreeding depression, the accumulation of harmful recessive genes that occurs when small populations reproduce over many generations. Studies suggest a minimum founding population of roughly 500 individuals to maintain genetic health across 10 generations, and even this may be insufficient for longer timescales. Some models propose populations of 10,000 or more to safely span hundreds of generations. Each person requires living space, agricultural area for food production, water recycling capacity, and waste processing. Conservative estimates suggest at least 100 square meters per person for living space alone, not including agricultural, industrial, and recreational areas. For 10,000 people, this means at least 1 million square meters, equivalent to a square kilometer of floor space. Multi-level designs reduce the footprint but require structural support and volume for infrastructure. The spacecraft would need to be truly gigantic, potentially several kilometers in length and hundreds of meters in diameter, massing millions of tons. Accelerating such a vessel to even modest interstellar velocities requires energy expenditures beyond current capabilities. Food production presents another seemingly insurmountable challenge. Humans can't survive on recycled nutrients alone. We require fresh food with complex micronutrients, fiber, and variety to maintain health. This means the ship must carry a complete ecosystem capable of sustained agriculture. Plants need light, water, nutrients, and atmosphere. Hydroponics or aeroponics systems reduce mass compared to soil-based agriculture, but still require infrastructure: pumps, lighting, nutrient delivery, climate control. Lighting alone becomes a major power demand. Plants require specific wavelengths in substantial intensity, and growing food for 10,000 people demands enormous illuminated area. Unless the ship uses external sunlight captured by massive mirrors, artificial lighting would consume megawatts continuously. Recycling water and air sounds straightforward but becomes complex at scale. The ISS recycles about 90% of water and 95% of oxygen, but it still requires periodic resupply because no system is perfectly efficient. A generation ship can't be resupplied; it must achieve near-perfect closure, recycling virtually every molecule indefinitely. Losses must be minimized to levels orders of magnitude below current technology. Every leak, every spill, every biological process that sequesters atoms into non-recyclable forms depletes the ship's reserves. Over centuries, even tiny losses accumulate into critical shortages. Maintaining a closed ecosystem also requires balancing countless variables: oxygen production versus consumption, carbon dioxide removal, nitrogen cycling, water purification, waste decomposition. Earth's biosphere handles these processes naturally through complex interactions among millions of species. Replicating even a fraction of this complexity in a spacecraft challenges current ecological understanding. Biosphere 2, an experimental closed ecosystem facility on Earth, struggled to maintain stable conditions for just 2 years, despite being far larger than any conceivable spacecraft and having direct access to sunlight and ground-based support. Sealed habitats experienced oxygen depletion, carbon dioxide accumulation, species extinctions, and crop failures. Scaling these lessons to interstellar generation ships suggests enormous difficulties. Mechanical systems also degrade over time. Every pump, valve, bearing, wire, circuit, and structural member experiences wear, fatigue, and eventually failure. On Earth, we replace worn parts with fresh components manufactured from raw materials. A generation ship must carry spare parts for every system, plus the manufacturing capability to produce new parts when spares run out. This requires raw material stockpiles, machine shops, foundries, electronics, fabrication, chemical processing, essentially a complete industrial base. The ship must be not just a habitat, but a self-sufficient industrial civilization capable of maintaining and repairing itself indefinitely without external resources. Social and governmental structures become critical. Who governs the ship? How are resources allocated? What happens when individuals or groups disagree with mission leadership? On Earth, dissatisfied populations can migrate or rebel. On a generation ship, there's nowhere to go. Authority must be maintained across generations without becoming tyrannical, yet preserving order and mission focus despite inevitable social tensions. Historical examples of isolated communities, remote islands, frontier settlements, religious colonies show how frequently governance breaks down into conflict, factionalism, or authoritarian control. A generation ship, with no escape and no external mediation, risks similar or worse outcomes, the Oort Cloud crossing. Even before a spacecraft reaches interstellar space proper, it must traverse the Oort Cloud, the vast spherical shell of icy debris marking the true outer boundary of our solar system's gravitational domain. This region, extending from roughly 2,000 astronomical units to nearly 100,000 astronomical units from the Sun, represents not just enormous distance but also a prolonged obstacle course lasting tens of thousands of years at any feasible spacecraft velocity. The Oort Cloud's existence is inferred rather than directly observed. Its objects are too small and distant to detect with current telescopes, reflecting too little sunlight to be visible. We know it exists because of long-period comets that arrive from random directions rather than along the plane of the planets. Their orbits traced backward to this distant reservoir. Estimates suggest the Oort Cloud contains trillions of objects, ranging from grains to mountain-sized chunks of ice and rock, with a total mass perhaps several times Earth's. These objects are spread across an incomprehensibly vast volume, making the average spacing between them hundreds of millions of kilometers. At first glance, this sparse distribution suggests collision risks are minimal. Space is mostly empty even here, but two factors complicate this reassuring picture. First, the spacecraft must traverse the entire shell, not just pass through one point. Even with vast spacing between objects, the probability of encountering something during a 50,000-year crossing becomes non-negligible. Second, we don't actually know the detailed distribution of Oort Cloud objects. Our understanding is based on models and the handful of long-period comets we've observed, a tiny, potentially biased sample. The cloud might contain denser concentrations or streams of material unknown to us. A spacecraft blindly crossing it could encounter hazards we haven't predicted. Detection and avoidance are nearly impossible at interstellar velocities. Even if the spacecraft carries powerful sensors capable of spotting objects ahead, the distances involved constrain reaction time. At 10% of light speed, the spacecraft covers 30,000 kilometers every second. Detecting an object 1 billion kilometers ahead, a distance that sounds vast, allows only about 9 hours to compute and execute an avoidance maneuver. Larger objects might be detected earlier, but smaller ones still capable of catastrophic damage at such velocities would be effectively invisible until too close to avoid. Maneuvering itself is problematic. Every course change requires propellant, and a spacecraft optimized for interstellar travel carries minimal fuel reserves beyond what's needed for primary acceleration and deceleration. Frequent avoidance maneuvers would quickly exhaust those reserves, leaving the craft unable to correct its trajectory or slow down at the destination. Mission planners would face a terrible choice: accept collision risk or carry extra fuel, which worsens the rocket equation and may render the mission impossible from the start. Protective shielding offers limited help. At 10% of light speed, even a small ice chunk carries immense kinetic energy. A 1 kilogram object about the size of a grapefruit impacts with energy equivalent to 20 tons of TNT exploding. A 10 kilogram object hits with 200 tons TNT equivalent. No practical armor can withstand such impacts. Whipple shields multiple spaced layers designed to fragment and disperse impacting objects, provide some protection against small debris, but fail catastrophically against larger pieces. Some designs propose active defense systems, lasers or projectile weapons to destroy approaching objects before they hit, but engaging targets at the required distances and velocities pushes the limits of plausibility. A laser must deliver enough energy to vaporize or deflect an object millions of kilometers away within the narrow window before impact. This requires knowing the object's composition, trajectory, and size with high precision information that's difficult to obtain for a distant, non-reflective chunk of ice. Vaporizing an object might also create a debris cloud that still impacts the spacecraft, trading one large hit for thousands of smaller ones. The timescale of Oort Cloud crossing means that spacecraft systems must operate reliably for tens of thousands of years, far beyond any current technological lifespan. The Voyager probes, our longest-lasting spacecraft, were launched in 1977 and remain partially functional now, but they'll be completely dead long before reaching the inner Oort Cloud. Designing systems that can self-maintain and self-repair across such timescales requires breakthroughs in material science, redundancy, and possibly artificial intelligence far beyond present capabilities. Micrometeorite erosion. Space debris isn't limited to large objects like asteroids or Oort cloud bodies. Interplanetary and interstellar space contain countless tiny particles, micrometeorites ranging from dust grains to sand-sized fragments. Near Earth, these particles rain down continuously, most burning up in the atmosphere before reaching the surface. In space, without atmospheric protection, spacecraft are constantly bombarded. At typical orbital velocities around Earth, roughly 7 to 8 kilometers per second, micrometeorite impacts pit and crater spacecraft surfaces, slowly degrading solar panels, antennas, and hull materials. Space stations and satellites must be designed with this erosion in mind. But at interstellar velocities, the problem transforms from gradual wear into catastrophic threat. The energy of impact scales with the square of velocity. At 10% of light speed, 30,000 kilometers per second, a micrometeorite hits with 4,000 times more energy than it would at Earth orbital velocity. A dust particle the size of a bacterium, utterly harmless at low speeds, carries as much kinetic energy as a rifle bullet. A grain of sand hits with the force of a grenade. Even individual atoms of interstellar gas, as discussed earlier, become damaging projectiles. At such velocities, impacting particles don't just dent or crater the hull, they vaporize on contact, releasing energy as an expanding plasma that melts and ablates surrounding material. Each impact creates a miniature explosion, flash heating the impact site to thousands of degrees and sending shockwaves through the spacecraft structure. Thousands or millions of such impacts per second, even from particles too small to see, gradually erode the leading surfaces of the spacecraft. Over years or decades, this erosion thins hulls, damages sensors, and degrades structural integrity. The rate of erosion depends on particle density along the spacecraft's path, a value we don't know with precision because interstellar space hasn't been extensively surveyed. The local interstellar medium near our solar system contains roughly 0.3 atoms per cubic centimeter and trace amounts of dust, but these values vary. Denser regions, molecular clouds, old supernova remnants, the outskirts of stellar nebulae could contain significantly more material. A spacecraft unlucky enough to pass through such a region would experience dramatically increased erosion and radiation, potentially fatal to the mission. Self-healing materials have been proposed as a solution, smart structures that can detect damage and repair themselves, perhaps using embedded reservoirs of material that flow into damaged areas and solidify. But such materials remain speculative and would add mass and complexity. They also can't heal indefinitely. Every repair depletes the reservoir until it's exhausted. Over tens of thousands of years, even slow erosion becomes catastrophic, and self-repair can't keep pace. Another approach is to make the spacecraft expendable in layers. Design it with sacrificial outer shells that absorb damage while protecting inner layers. As the outer shell erodes away, the next layer takes over. This extends functional lifespan, but requires enormous initial mass. Each protective layer must be accelerated along with the rest of the vehicle, worsening the rocket equation. And eventually, all layers are exhausted and the core spacecraft is exposed. Dust grain impacts also generate secondary radiation. When a grain vaporizes on impact, it creates a plasma containing ionized atoms and high-energy photons. This flash of radiation propagates into the spacecraft, potentially damaging electronics and biological tissue. Unlike cosmic rays, which arrive from all directions, this secondary radiation is concentrated along the spacecraft's direction of travel, making frontal shielding more effective, but also concentrating wear on those forward surfaces. The return journey problem. Most discussions of interstellar travel focus on reaching another star, but a complete mission profile must address the return journey getting back to Earth. For uncrewed probes, this may be unnecessary. We can design them as one-way missions that transmit data back via radio signals. But for human exploration or colonization missions where return is desired, the return journey doubles every problem we've discussed. The spacecraft must carry fuel not just to reach the destination but to decelerate there, then accelerate back toward Earth, then decelerate again upon arrival. Each of these maneuvers requires propellant, and the rocket equation compounds at each stage. Consider a simple example. A spacecraft using conventional propulsion needs fuel to accelerate toward Alpha Centauri. It also needs fuel to slow down when it arrives, otherwise it simply flies past at high speed. This deceleration fuel must be carried during the acceleration phase, so you need even more fuel at the start to accelerate the deceleration fuel. Then, for the return journey, you need fuel to accelerate back toward Earth and fuel to decelerate upon arrival. And all of that return fuel must be carried from Earth during the initial launch, requiring still more fuel to accelerate it during the outbound leg. The mass ratios spiral toward absurdity. With chemical rockets, the fuel mass required exceeds the mass of the observable universe. Even with advanced propulsion, nuclear or fusion drives, the ratios become prohibitively large, rendering round-trip missions effectively impossible unless we can refuel at the destination. Refueling at the destination sounds reasonable until you examine the logistics. It requires finding or creating fuel sources in the target star system, extracting hydrogen from a gas giant's atmosphere, mining ice from comets, or processing local materials into propellant. This requires infrastructure, mining equipment, refining facilities, storage tanks, and probably a base or settlement to house the workers or robots performing these tasks. Building such infrastructure requires sending it ahead on a separate mission, which itself needs fuel and becomes subject to the same rocket equation problems. You end up needing to establish an entire industrial base in another star system before attempting a crude round-trip mission, a chicken-and-egg problem that pushes timelines and costs into fantasy territory. Alternatively, we could imagine sending the return fuel in advance on a slower cargo mission, launch a fuel depot toward Alpha Centauri decades or centuries before the crewed mission, let it drift there slowly with minimal propulsion, then have the crew rendezvous with it upon arrival. But this requires the fuel depot to arrive successfully, remain functional across the transit time, and be located precisely where the crew can find it, a daunting navigation challenge across interstellar distances. If the depot drifts off course or malfunctions, the crew is stranded with no way home. For missions without return, one-way trips where humans travel to another star system intending to stay permanently, the psychological and ethical implications are profound. You're asking people to leave Earth forever, knowing they'll never return, never see home again, and likely never communicate meaningfully with anyone left behind due to the decades-long signal delays. This might appeal to pioneers or those with nothing to lose, but recruiting enough volunteers with the skills necessary to establish a colony in a hostile environment would be difficult. And funding such missions politically requires convincing taxpayers or investors to spend vast resources on projects with no direct benefit to Earth. No returning astronauts to parade, no samples brought back, no tangible evidence of success beyond faint radio signals arriving years after the fact. The return journey also compounds time dilation problems. If the outbound journey takes decades from Earth's perspective, but only years for the crew due to relativistic effects, the return journey adds another set of decades, meaning crew members arrive home perhaps a century or more after they departed. Everyone they knew would be dead, society would have changed beyond recognition, and they'd essentially be time travelers visiting a future world. This makes the mission psychologically similar to a one-way trip, even if the spacecraft physically returns. The deceleration dilemma. Accelerating a spacecraft to interstellar velocities represents only half the journey's propulsion challenge. The other half, arguably the more difficult half, is slowing down at the destination. A probe screaming through space at 10% of light speed carries enormous kinetic energy, and eliminating that energy to achieve orbit or landing requires forces and fuel masses comparable to what was needed for acceleration. Without deceleration, the spacecraft becomes merely an extremely fast tourist, glimpsing its target star system for hours or days before shooting past into the void beyond, its mission a failure despite decades or centuries of travel time. The physics of deceleration mirror those of acceleration, but with added complications. During the initial acceleration phase departing Earth, the spacecraft can jettison spent fuel tanks and stages, reducing mass as it goes, the principle behind multi-stage rockets. But deceleration requires carrying all the braking fuel from the beginning, adding to the mass that must be accelerated in the first place. This creates a vicious recursion. More braking fuel means more mass to accelerate, which means more acceleration fuel, which means more mass to brake, which means more braking fuel. The rocket equation compounds exponentially at each step. Consider a 1-ton probe traveling to Alpha Centauri at 10% of light speed. To decelerate using conventional chemical propulsion would require fuel masses measured in trillions of tons more than the mass of Earth itself. Even with advanced nuclear propulsion offering exhaust velocities 10 times higher, the fuel requirements remain impossibly large. Ion drives, with their high exhaust velocities, fare better mathematically, but produce such minuscule thrust that deceleration would take centuries, during which the spacecraft continues traveling farther from its target, making the maneuver pointless. Alternative deceleration methods have been proposed, each with severe limitations. Magnetic sails could theoretically catch the target star's stellar wind, the stream of charged particles flowing outward from the star. By deploying a large electromagnetic loop generating a powerful magnetic field, the spacecraft could create drag against this wind, gradually slowing over months or years. But stellar winds are tenuous, providing minimal braking force. The magnetic sail would need to be enormous kilometers in diameter, and the deceleration zone would extend across billions of kilometers. The spacecraft would begin braking while still far from the star system, potentially missing the intended target orbit. Another concept involves using a light sail in reverse. During acceleration, ground-based lasers push against a reflective sail to accelerate the craft. For deceleration, a laser array at the destination built by a previous mission or by automated infrastructure sent ahead would fire at the incoming spacecraft, pushing against its sail to slow it down. This eliminates the need to carry braking fuel but creates new problems. The laser array must be operational decades or centuries after being deployed, requiring self-maintaining systems of daunting complexity. It must track and target a spacecraft traveling at relativistic velocities, hitting it with sufficient precision to push against the sail rather than missing entirely or damaging the craft. And the energy requirements are staggering megawatts or gigawatts of laser power sustained for months or years. Aerobraking using a planet's atmosphere to slow down through friction works well for interplanetary missions, but becomes problematic at interstellar velocities. A spacecraft traveling at 10% of light speed carries so much kinetic energy that atmospheric entry would generate temperatures exceeding anything materials can withstand. The craft would vaporize almost instantly, creating a meteor bright enough to be seen from the surface, but achieving no useful deceleration. Even if advanced heat shields could somehow survive, the deceleration forces would be extreme hundreds or thousands of Gs, pulverizing any payload and likely breaking the spacecraft apart. Gravitational assists provide another theoretical option. Spacecraft routinely use planetary flybys to alter velocity, stealing a tiny amount of the planet's orbital momentum, but the velocity changes achievable this way are small, typically a few kilometers per second at most. To decelerate from 30,000 kilometers per second using gravitational assists would require dozens or hundreds of carefully timed flybys of planets or stars, and the geometry rarely aligns conveniently. Arranging such a series of encounters would demand extraordinary precision in navigation and timing, likely taking decades or centuries to complete, during which the spacecraft continues moving through the target system rather than settling into useful orbit. Some mission concepts simply abandon deceleration entirely, designing probes as high-speed flybys. As the spacecraft screams through the system at relativistic velocity, it takes rapid-fire measurements, images, and samples during the brief window when instruments can observe the target. All data must be collected in hours or days and transmitted back to Earth immediately, because the probe continues past the star system and never returns. This approach wastes most of the transit time, decades or centuries spent traveling, for hours of useful science. The data return is also limited. There's no opportunity for follow-up observations, detailed surface mapping, or long-term monitoring. A single flyby provides merely a snapshot, leaving countless questions unanswered. The mass-energy equations for deceleration become even more punishing when considering crewed missions. Human passengers require life support throughout the braking phase, which could last years if gentle deceleration is needed to avoid lethal G-forces. During this time, the spacecraft must provide air, water, food, and radiation shielding, while still maneuvering. The additional mass of these systems, plus the mass of the crew itself, multiplies the fuel requirements beyond any reasonable limit. Deceleration also creates thermal management nightmares. Whether using rocket engines, atmospheric friction, or magnetic drag, the process converts kinetic energy into heat, enormous quantities of heat that must be radiated away. A 1-ton spacecraft braking from 10% of light speed must dissipate roughly 4.5 times 10 to the power of 17 joules. Even spread over months, this heat flux would melt most materials. Radiator systems capable of handling such loads would need to be huge, adding more mass to an already impossible equation: cosmic ray degradation of electronics. While biological radiation exposure poses severe risks to living crew members, cosmic rays also threaten the electronic systems essential for spacecraft operation. These high-energy particles don't just pass harmlessly through circuits, they interact with semiconductor materials in ways that corrupt data, damage components, and gradually degrade performance until systems fail entirely. For missions lasting decades or centuries, cosmic ray damage to electronics represents an insidious threat that accumulates relentlessly, eventually rendering the spacecraft inoperable, regardless of how well other systems function. The mechanisms of radiation damage to electronics are well understood from decades of operating satellites and space probes. Single-event upsets occur when a cosmic ray strikes a memory cell, flipping a bit from 0 to 1 or vice versa. In isolation, a single flipped bit might corrupt one calculation or alter one byte of data, annoying but not catastrophic. But computers perform billions of operations per second, and memory contains millions or billions of bits. Cosmic rays strike continuously, causing upsets at rates that depend on the radiation environment and the specific chip architecture. In deep space, far from Earth's protective magnetosphere, upset rates increase dramatically. Error-correcting codes can detect and fix some bit flips by storing redundant information and using mathematical algorithms to identify corrupted data. Space-rated computers employ error correction extensively, accepting the overhead of extra memory and processing time to maintain data integrity. But error correction has limits. It can fix a certain number of errors per data block, but fails if too many bits flip simultaneously or if errors accumulate faster than they can be corrected. Cosmic rays don't arrive in steady, predictable streams, they come in bursts and clusters, especially during solar particle events or when passing through regions of space with higher radiation flux. A cluster of hits in quick succession can overwhelm error correction, causing unrecoverable data corruption. More serious than bit flips are single-event latch-ups and burnouts, where cosmic ray strikes trigger failure modes that permanently damage the chip. A latch-up occurs when radiation creates a conductive path through the semiconductor, allowing excessive current to flow. This current can overheat and destroy internal structures if not detected and interrupted quickly by protective circuitry. A burnout involves direct destruction of transistor gates or interconnects, creating permanent open or short circuits. These failures are irreversible, the affected chip is dead and must be replaced. Over decades or centuries, cumulative damage from burnouts gradually erodes the spacecraft's computing capability as more and more circuits fail. Total ionizing dose represents another degradation mechanism. As radiation passes through electronic components, it deposits energy in insulating layers, the oxide films that separate transistors and wiring in integrated circuits. This energy creates electron-hole pairs and trapped charges that alter the electrical properties of the oxide, changing transistor behavior. Transistors might switch more slowly, leak more current, or stop functioning altogether as threshold voltages drift beyond design tolerances. Unlike single-event effects, total dose damage accumulates gradually, proportional to the total radiation exposure over time. For short missions lasting months or a few years, total dose effects can be managed by using radiation-hardened components designed to tolerate megarads of exposure. But interstellar missions accumulate dozens over decades or centuries, eventually exceeding even radiation-hardened specifications. There's no way to reset or repair total dose damage, it's cumulative and permanent. Eventually, enough transistors drift out of specification that the chip fails. Shielding electronics provide limited protection. While physical barriers can stop some particles and reduce radiation intensity, they also generate secondary radiation when struck by cosmic rays. As discussed earlier, dense materials like lead actually worsen the problem by producing more secondaries. Lighter materials like polyethylene or water provide better protection per unit mass. but shielding the entire spacecraft's electronics requires massive amounts of material, adding weight and worsening the propulsion challenge. Redundancy offers a partial solution. Critical systems can be duplicated or triplicated, with majority voting logic selecting the correct output when components disagree. If one computer suffers a radiation-induced error, the other two outvote it, maintaining correct operation. When a component fails permanently, the system switches to a backup, but redundancy adds mass, consumes more power, increases complexity, and merely delays the inevitable. Eventually, all redundant units suffer enough damage that the system fails entirely. Radiation doesn't discriminate, it affects all components equally, so primaries and backups degrade at similar rates. Some proposed solutions involve using analog electronics instead of digital, arguing that analog circuits are more radiation tolerant since they don't rely on precise voltage thresholds and binary logic. But analog electronics are less capable, harder to program, and more susceptible to noise and drift from other sources. Modern spacecraft require sophisticated computing for navigation, communication, data processing, and autonomy tasks poorly suited to analog systems. Another concept suggests using optical computing based on photons rather than electrons, potentially immune to radiation-induced upsets. But optical computers remain experimental, are difficult to miniaturize, and consume more power than electronic equivalents. Manufacturing them with space-rated reliability would require decades of development. The radiation environment varies along different trajectories. Missions passing near Jupiter encounter intense radiation trapped in the planet's magnetosphere, electron and proton belts far more hostile than Earth's Van Allen belts. Voyager, Galileo, and Juno spacecraft all suffered radiation damage during Jupiter operations, with components failing earlier than expected. An interstellar mission might route around such hazards, but some radiation is unavoidable everywhere in space. The unshielded solar wind problem. Within the heliosphere, the bubble of space dominated by the sun's magnetic field, and solar wind spacecraft experience some natural protection from galactic cosmic rays. The solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second, carries embedded magnetic fields that deflect some incoming cosmic rays, reducing their intensity. This modulation effect varies with the solar cycle. During solar maximum, when the wind is strongest and most turbulent, cosmic ray intensity decreases by roughly 20% compared to solar minimum. The heliosphere acts as a partial shield, not stopping cosmic rays entirely but reducing their flux compared to true interstellar space. But interstellar missions must eventually cross the heliopause, the boundary where the solar wind stops and interstellar medium begins. Voyager 1 crossed this boundary in 2012 at roughly 122 astronomical units from the Sun, and Voyager 2 followed in 2018. Beyond the heliopause lies the true interstellar medium, where the Sun's protective influence ends and cosmic ray intensity increases. Measurements from both Voyager probes confirm that cosmic ray flux jumps significantly, roughly 40% once outside the heliosphere. This increase represents the loss of solar modulation, exposing spacecraft to the full intensity of galactic cosmic radiation. For missions traveling toward other stars, this means the most dangerous radiation environment occurs precisely where they'll spend the vast majority of their journey time. The relatively brief passage through the heliosphere provides minimal protection, while decades or centuries in interstellar space subject all systems and crew to maximum radiation exposure. Unlike trapped radiation belts around planets, which can be avoided by careful trajectory planning, the elevated cosmic ray flux of interstellar space is omnipresent and inescapable. The transition itself also presents challenges. The heliopause isn't a sharp boundary, but a turbulent transition region where solar wind, interstellar plasma, and magnetic fields interact chaotically. This boundary layer, tens of astronomical units thick, creates unpredictable variations in particle flux and energy spectrum. Spacecraft instruments must adapt to rapidly changing conditions, and navigation might become more difficult as the familiar reference provided by solar wind measurements vanishes. The Sun's protective influence weakens with distance, even before reaching the heliopause. At Jupiter's distance, 5 astronomical units, solar wind modulation remains strong, but by the time a spacecraft reaches the outer planets and beyond, the effect diminishes substantially. A mission traveling outbound through the solar system experiences gradually increasing radiation exposure, starting well before it officially enters interstellar space. By the time it passes Neptune's orbit at 30 astronomical units, radiation intensity has increased noticeably, and crew or systems begin accumulating faster than they would near Earth. Solar particle events, brief, intense bursts of radiation from solar flares and coronal mass ejections, actually become less dangerous at interstellar distances, simply because the spacecraft is too far for these localized events to reach it effectively. Solar particles travel at speeds much slower than cosmic rays, typically millions of miles per hour rather than near light speed, and they spread out and weaken with distance. A powerful solar storm that would deliver lethal doses to astronauts near Earth becomes negligible by the time its effects reach the heliopause. So while baseline cosmic ray exposure increases in interstellar space, the worst spikes associated with solar activity disappear, creating a trade-off where average exposure rises but variability decreases. This has implications for mission planning. Spacecraft departing the solar system might intentionally launch during solar maximum, when the enhanced solar wind provides maximum cosmic ray shielding for the inner solar system phase of the journey. By the time they reach interstellar space and lose this protection, they're already committed to the mission and beyond any point of return. But the solar cycle lasts only 11 years, a blink compared to interstellar transit times, so the timing provides marginal benefit at best. The loss of solar wind also affects other spacecraft systems. The wind carries the interplanetary magnetic field, which can be measured to determine the spacecraft's orientation relative to the Sun, useful for navigation when the Sun remains visible. In interstellar space, this magnetic reference disappears, requiring alternative attitude determination methods. Some spacecraft use star trackers, cameras that identify patterns of stars and calculate orientation by comparing observations to catalogues. But star trackers require power, add mass, and depend on complex software that might fail over long timescales. The gravity well problem at both ends. Earth's deep gravity well requires enormous energy to escape. Launching payloads into low Earth orbit demands velocities of roughly 7-8 kilometers per second. Escaping Earth's gravity entirely requires 11.2 kilometers per second. Reaching interstellar velocities adds still more. These energy requirements create a fundamental bottleneck at the beginning of any interstellar mission, limiting how much mass we can send regardless of propulsion technology. Current launch systems, chemical rockets like Falcon Heavy, Delta IV Heavy, or SLS, can place roughly 60 to 130 tons into low Earth orbit per launch. Sending mass beyond Earth orbit reduces payload capacity dramatically. A Mars mission might deliver 10 to 20 tons to Mars transfer orbit. An interstellar probe would need to achieve far higher velocities, reducing launchable mass to a few tons at best using conventional staging. And those few tons must include all structure, fuel for further acceleration, power systems, communication equipment, instruments, and payload. The mass budget becomes impossibly tight. Advanced launch systems like space elevators, orbital rings, or mass drivers could potentially reduce launch costs and increase payload mass by eliminating the rocket equation's tyranny during the climb out of Earth's gravity well. But these systems require massive infrastructure investment and technological breakthroughs that remain speculative. A space elevator, for instance, requires materials with tensile strength far exceeding anything currently available. Carbon nanotubes have the theoretical strength, but manufacturing macroscopic cables from them remains beyond current capabilities. Even if we could build such systems, their construction would take decades and consume resources equivalent to major national economies. The gravity well problem doesn't end on Earth. The target star system almost certainly has its own gravity well. If the mission objective includes exploring planets, the spacecraft must decelerate enough to enter orbit, not just around the star, but around specific planets. This requires additional fuel beyond what's needed to stop relative to the star itself. A spacecraft arriving at Alpha Centauri, traveling at 10% of light speed, needs to shed nearly all that velocity to achieve stellar orbit, then perform additional burns to transfer to planetary orbit, and potentially more fuel to land on surfaces or position instruments. Each maneuver demands propellant, and all that propellant must be carried from Earth or obtained locally. Local fuel acquisition sounds promising, but faces chicken and egg problems discussed earlier. You need infrastructure to extract and process fuel, but deploying that infrastructure requires a mission that already has fuel to get there. Pre-positioning fuel depots, or refining equipment on slow cargo missions, requires those missions to carry their own fuel for the journey, reproducing the same problem one step removed. Gravity assists can help navigate within a star system once you're there, using planetary flybys to alter trajectory and save fuel. But setting up useful gravitational assist sequences requires detailed knowledge of planet positions and orbits information we generally lack for exoplanet systems. Most detected exoplanets are found via transits or radial velocity methods that reveal their existence and rough orbital parameters, but not precise positions at any given time. Navigating a gravity assist sequence without accurate ephemerides would be like threading a needle blindfolded. The Sun's gravity well also affects departure trajectories. Launching directly outward from Earth on an interstellar trajectory wastes energy fighting both Earth's and the Sun's gravity. More efficient trajectories first perform a burn to dive toward the Sun, gaining velocity as the spacecraft falls inward, then execute a high-speed turn at perihelion closest approach, where gravitational and kinetic energy combine to maximum effect. This Oberth maneuver exploits the principle that burning propellant at high velocity produces more effective velocity change than burning at low velocity, but it requires heat shielding to survive close solar approach and precise navigation to avoid overshooting or colliding with the Sunday. Jupiter assists have been used by many deep space missions, Voyager, Galileo, New Horizons, to gain velocity leaving the solar system. A close flyby of Jupiter can add several kilometers per second to spacecraft velocity, essentially for free, stealing a tiny fraction of Jupiter's enormous orbital momentum. But even this substantial boost provides only a small fraction of the velocity needed for rapid interstellar transit. Jupiter assist might help a probe reach 20 or 30 kilometers per second relative to the Sun, enough to cross the solar system in years rather than decades, but still falls short of the thousands of kilometers per second needed for practical interstellar missions. The cosmic void temperature problem. Space is cold, not in the sense of wind chill or winter storms, but in the more fundamental sense that it contains very little thermal energy per unit volume. Far from stars, the temperature of space itself approaches the cosmic microwave background radiation temperature of 2.7 Kelvin, just a few degrees above absolute zero. For spacecraft systems, this extreme cold presents challenges as severe as radiation or micrometeorites, threatening to freeze propellants, crack materials, and shut down electronic systems unless active heating maintains operational temperatures. But the cold creates a paradoxical problem. While space is extremely cold, it's also an excellent insulator. On Earth, objects lose heat through conduction, convection, and radiation. In the vacuum of space, conduction and convection don't exist. There's no air or material to carry heat away. The only heat loss mechanism is thermal radiation, which becomes dramatically less efficient at low temperatures. An object at room temperature radiates heat slowly in space, far more slowly than it would on Earth in a freezer. This means spacecraft have difficulty both staying warm and getting rid of excess heat, depending on their operational state and distance from the Sunday. Near Earth, the Sun provides abundant heat. Spacecraft must actually work to avoid overheating, using radiators to dump excess thermal energy. But at interstellar distances, the Sun becomes just another star, providing negligible warmth. Active systems, computers, transmitters, scientific instruments, generate some waste heat during operation. But when systems shut down for power conservation, temperatures plummet, batteries freeze and become useless, propellants solidify, mechanical joints contract and seize, materials become brittle and crack under stress. Maintaining temperature requires power heaters that consume electricity to keep critical systems warm. But power is the scarcest resource on interstellar missions. Solar panels don't work where sunlight is negligible. RTGs decay over time, providing less power as decades pass. Every watt spent on heating is a watt unavailable for propulsion, communication, or science. Mission designers must perform ruthless power budgets, determining which systems can be allowed to freeze and which must be kept warm at all costs. Some systems can tolerate freezing if warmed up before use, but thermal cycling repeated heating and cooling degrades materials and connections. After hundreds or thousands of thermal cycles over decades, cumulative damage renders systems inoperable, even if they never experienced outright failure. Components must be over-engineered to survive this cycling, adding mass and complexity. Cryogenic propellants face severe storage challenges. Liquid hydrogen and oxygen, commonly used in rocket engines, boil at 20 Kelvin and 90 Kelvin respectively. In deep space, the cosmic background temperature of 2.7 Kelvin is well below these boiling points, so cryogenic propellants should remain liquid indefinitely without need for refrigeration. But in practice, any heat input from waste heat from nearby systems, from solar radiation in the outer solar system, or from cosmic rays deposits energy causes slow boil-up. The propellant gradually evaporates, increasing tank pressure until relief valves must vent the gas overboard. Each venting episode loses propellant, slowly depleting the spacecraft's fuel reserves over time. Long-term cryogenic storage has never been demonstrated for decades, let alone centuries. Alternative propellants, like storable hypergolics, don't freeze, they remain liquid at room temperature and below. But they're less energetic than cryogenic options, offering lower exhaust velocity and worsening the rocket equation. They're also corrosive and toxic, requiring careful containment and handling. Thermal radiation becomes less effective at lower temperatures, following the Stefan Boltzmann law, radiated power scales with the fourth power of absolute temperature. An object at 300 Kelvin radiates 16 times more power per unit area than an object at 150 Kelvin. This creates problems for getting rid of unwanted heat even as it helps retain desired warmth. A spacecraft generating waste heat from nuclear reactors or high-power transmitters must maintain high radiator temperatures, hundreds of Kelvin, to radiate efficiently. But keeping radiators hot while the surrounding space is at 2.7 Kelvin requires careful thermal management and significant radiator surface area. The interstellar particle collision problem. Earlier sections discussed micrometeorite erosion and the interstellar medium as sources of gradual damage. But another particle threat deserves specific attention: the possibility of catastrophic collision with objects large enough to destroy the spacecraft outright, but too small to detect in advance. This threat occupies an uncomfortable middle ground bigger than dust grains that merely erode surfaces, but smaller than asteroids that might be detected and avoided. In this size range, typically millimeters to centimeters, objects carry sufficient mass that impact at relativistic velocities, releases energy comparable to nuclear weapons. At 10% of light speed, a 1-gram object about the mass of a paperclip carries kinetic energy equivalent to 21 kilograms of TNT. A 10-gram object hits with 210 kilograms TNT equivalent. A 100-gram object, roughly the mass of a bar of soap, impacts with 2.1 tons of TNT, comparable to a large conventional bomb. These aren't hypothetical calculations. They're direct consequences of the kinetic energy equation. And such objects exist in space. Micrometeorites span a wide size range, from nanometer-scale grains to centimeter-scale chunks. Most are tiny, but the size distribution includes larger specimens. The exact distribution of particle sizes in interstellar space remains poorly characterized because we've only sampled a tiny region near our solar system. Interplanetary space contains debris from asteroid collisions, comet outgassing, and planetary formation. But interstellar space hasn't been surveyed in detail. Models suggest lower densities than in planetary systems, no asteroid belt to generate debris, no comets to shed ice particles, but also acknowledge huge uncertainties. The spacecraft might traverse regions with higher than expected particle density, or encounter debris clouds from ancient stellar processes unknown to current astrophysics. Detection of hazardous particles at interstellar distances faces severe limits. Optical systems can potentially spot objects by reflected starlight, but the objects must be large enough and reflective enough to return detectable signals. A dark, irregular chunk of rock or ice might reflect too little light to be visible until it's dangerously close. Radar could detect smaller objects by bouncing radio waves off them, but this requires the spacecraft to carry radar transmitters powerful enough to illuminate objects at sufficient range, thousands or millions of kilometers ahead, and sensitive receivers to detect the faint return echoes. Such systems consume power and add mass. Even if detection works, avoidance requires maneuvering, which consumes propellant. A spacecraft optimized for interstellar velocity dedicates most of its fuel to primary acceleration and reserves minimal amounts for course corrections. Frequent dodging maneuvers would exhaust this reserve, leaving the craft unable to correct its overall trajectory. and the detection response timeline is compressed by the high velocity. At 30,000 kilometers per second, detecting an object 1 million kilometers ahead allows only 33 seconds to calculate a response and execute the maneuver. Autonomous systems must react faster than human operators could possibly intervene. Armoring against such impacts requires enormous mass. At relativistic velocities, even advanced materials can't stop centimeter-scale objects. Whipple shields multiple spaced layers designed to fragment and vaporize impactors before they reach critical systems. Work well for debris at orbital velocities, but become less effective as impact speed increases. Each layer must be thick enough to disrupt the impactor while being light enough that the overall shield remains launchable. The trade-off becomes impossible at interstellar velocities. Effective shielding would weigh more than the rest of the spacecraft. Statistical risk assessment provides some comfort. Space is vast, and even in relatively dense regions, most of the volume contains nothing. The probability of encountering a dangerous-sized object during transit might be low, perhaps a few percent over the entire journey. But low probability over decades or centuries still adds up to significant cumulative risk. A 1% chance per century becomes a 22% chance over 25 centuries. For crewed missions, such odds are unacceptable. Asking astronauts to accept a 1 in 5 chance of catastrophic collision would be ethically and politically impossible. The problem of unknown unknowns. All previous barriers discussed rocket equation, radiation, navigation, power, temperature, derive from known physics and observed conditions. These are known unknowns. We understand the problems and can quantify the challenges even if we can't yet solve them. But interstellar space also presents unknown unknowns. Phenomena we haven't yet discovered because we've never traveled there. Our understanding of conditions beyond the solar system relies on remote observations, theoretical models, and data from 2 Voyager probes that have barely crossed the heliopause. Beyond that narrow sampling lies a vast, unexplored volume where unexpected hazards might lurk. History provides cautionary examples. Before spacecraft visited other planets, models predicted surface conditions based on telescope observations and theory. Those predictions were often dramatically wrong. Venus was thought to be temperate, possibly habitable, until Venera probes revealed surface temperatures hot enough to melt lead and atmospheric pressure 90 times Earth's. Mars was believed to have seasonal vegetation until Mariner probes showed a cold, dead desert. Jupiter's radiation belts proved far more intense than expected, crippling several probes. Conditions in space routinely surprise us, and we've only explored our immediate neighborhood. Interstellar space may contain structures or phenomena invisible from Earth. Molecular clouds, vast regions of dense gas, can't be detected unless they emit radio signals or block background stars. A spacecraft could fly into such a cloud without warning, encountering drastically increased particle density and radiation. The drag from dense gas might slow the craft or heat it beyond design limits. Unforeseen chemical reactions between spacecraft materials and cloud constituents might corrode or damage systems. Magnetic field structures could pose unexpected challenges. The Sun generates a heliosphere, a bubble of magnetized solar wind, extending hundreds of astronomical units. Other stars surely generate similar structures, and the space between stars may contain remnant magnetic fields from ancient supernovae or large-scale galactic field lines. These fields might be stronger or more complex than models predict. A spacecraft carrying sensitive magnetometers or using magnetic navigation could be disrupted. If the craft uses magnetic sails for braking or course correction, unexpected field strengths might produce excessive forces or insufficient drag. Dust lanes and debris fields might exist in interstellar space, remnants of long-ago stellar collisions or disrupted star systems. Our solar system contains the asteroid belt and Kuiper belt regions of concentrated debris. Who's to say interstellar space doesn't have similar structures? Invisible from Earth, because they're too diffuse or dark to detect. A spacecraft blundering into such a region would face suddenly elevated collision risk without warning. Gravitational anomalies represent another unknown. General relativity predicts that mass warps spacetime, and large masses create measurable gravitational effects. But dark matter, which dominates galactic mass, remains mysterious. We know it exists through its gravitational effects on visible matter, but we don't know its distribution on smaller scales. Clumps or streams of dark matter could create gravitational perturbations that alter spacecraft trajectories. While dark matter doesn't interact electromagnetically and can't be collided like ordinary matter, its gravity affects everything passing nearby. Unexpected gravitational tugs might pull the spacecraft off course, requiring fuel-consuming corrections, or worse, disrupting carefully planned gravitational assists or braking maneuvers. Exotic particles or radiation types might exist but remain undetected because they interact so weakly with matter that our instruments don't register them or register them as background noise. Neutrinos, for example, pass through Earth almost without interacting at all. Trillions pass through your body every second without effect. But more exotic particles might exist with subtle effects that accumulate over long timescales. Decades or centuries of exposure to unknown radiation types could degrade materials or electronics in unexpected ways. Even the nature of space itself might differ in interstellar regions. Quantum field theory describes the vacuum as seething with virtual particles and fields. But these effects are typically negligible at macroscopic scales. Yet in the near-perfect vacuum between stars, traversed at relativistic velocities over vast timescales, exotic quantum effects might become relevant. We simply don't know because we've never tested those conditions. One humbling fact should temper confidence in our models. We still don't fully understand the solar system after decades of intensive study. New Horizons discovered unexpected features on Pluto. The Juno mission revealed Jupiter's interior is more complex than models predicted. Voyager found the heliopause in an unexpected location and shape. If we're still learning about our own cosmic backyard, how can we be confident about conditions light years away? The multi-generational genetic collapse. Beyond the engineering impossibilities and physical barriers, stands another fundamental obstacle to interstellar colonization. The biological reality of small populations isolated for thousands of years. Even if we solved every propulsion problem, overcame radiation exposure, and maintained spacecraft systems indefinitely, a crew of any feasible size faces inevitable genetic degradation through a process called inbreeding depression. The mathematics of population genetics aren't suggestions they're biological laws as rigid as physics, and they doom any attempt to send viable breeding populations across interstellar distances. Population geneticists have studied isolated populations extensively, from island species to captive breeding programs, and the results are unambiguous. Small populations lose genetic diversity rapidly through two mechanisms: genetic drift and inbreeding. Genetic drift occurs because not every individual in a generation passes on their genes. Some die before reproducing. Others have fewer offspring than average. This random sampling means rare genetic variants disappear quickly in small populations simply by chance. Over time, the gene pool shrinks, eliminating beneficial variations that might be crucial for adapting to new environments or resisting diseases. Inbreeding, mating between relatives, becomes mathematically inevitable in small, isolated populations. Even if cultural taboos prohibit sibling or parent-child pairings, more distant relationships accumulate unavoidably. Third cousins become second cousins in subsequent generations, then first cousins, until the entire population becomes related at levels that would be considered incestuous in open populations. This relatedness means that recessive deleterious alleles, harmful genetic variants, masked in the general population by healthy dominant versions, become expressed when both parents carry the same variant. Birth defects, genetic diseases, reduced fertility, and lower immune function all increase as inbreeding intensifies. The minimum viable population for long-term survival depends on mission duration. For a journey lasting 10 generations, roughly 250 years for humans, population geneticists estimate a minimum of 160 individuals, and preferably 500, to maintain genetic health and avoid inbreeding depression. These numbers assume perfect breeding management, carefully planned pairings to maximize genetic diversity, comprehensive genetic screening to identify and avoid pairing carriers of harmful recessive alleles, and compliance from all participants. Such management might work for a few generations, while the original mission remains culturally important, but maintaining it for dozens or hundreds of generations becomes increasingly implausible as social cohesion weakens and original purpose fades. For truly interstellar journeys lasting thousands of years necessary to reach stars more than a few dozen light-years away, at sublight speeds the required population grows dramatically. Some models suggest 40,000 individuals minimum to maintain genetic viability across 400 generations. A spacecraft housing 40,000 people with all necessary life support, agriculture, industry, and living space would be a flying city kilometers in scale, massing millions of tons. Accelerating such a vessel to interstellar velocities requires energy beyond any conceivable power source. The rocket equation kills the concept before genetic concerns even become relevant. Genetic load, the accumulation of deleterious mutations in a population, increases faster in small populations because purifying selection becomes ineffective. Each individual carries hundreds of mildly harmful variants, masked by having one good copy of each gene. In small populations, these variants become homozygous more frequently, expressing their harmful effects and reducing fitness. Over generations, genetic load accumulates until average fitness declines noticeably. Fertility drops, infant mortality rises, lifespans shorten, and susceptibility to disease increases. This process, called mutational meltdown, can drive small populations to extinction even in stable environments. Cryogenic preservation of sperm, eggs, or embryos offers a potential solution, launching frozen genetic diversity to be thawed and used gradually over generations, introducing fresh genes into the breeding pool. But cryogenic storage for centuries or millennia remains unproven. Will frozen samples remain viable after 500 years? 1,000 years? Nobody knows because we haven't tested such durations. Cosmic radiation might damage frozen cells despite shielding. Equipment failures could thaw samples prematurely. And managing a breeding program that incorporates thawed genetic material requires sophisticated technology and social organization maintained across dozens of generations, itself a dubious assumption. Even with perfect genetic management, demographic stochasticity threatens small populations. Random variation in birth rates, sex ratios, and mortality creates fluctuations that matter more as population size decreases. A generation with more male births than female, or a disease outbreak that kills disproportionately from one sex or age group, can create demographic imbalances that take generations to correct or might initiate a downward spiral toward extinction. Historical examples abound. Many isolated human populations have gone extinct, not from resource depletion, but from demographic and genetic misfortune. The founder population's genetic origin also matters. Selecting crew from diverse ethnic backgrounds maximizes initial genetic variation, but this creates social and cultural challenges. Alternatively, selecting crew from similar backgrounds for social cohesion sacrifices genetic diversity. There's no solution that optimizes both variables simultaneously. The mission must choose between maximizing biological viability and social stability, and neither choice guarantees success. Upon arrival at the destination, assuming the population survives the journey genetically intact, they face new challenges. Establishing a viable colony on an exoplanet requires expanding the population rapidly to create a stable genetic base. But this requires resources, living space, and environmental conditions that support reproduction and child-rearing. If conditions are harsh or resources scarce, population growth stalls and the genetic bottleneck persists, potentially for many generations, continuing to erode diversity. The mathematical reality is stark. Interstellar colonization requires either enormous populations, tens of thousands of people making the spacecraft impossible to build and launch, or small populations that face inevitable genetic degradation and likely extinction within dozens of generations. There's no middle ground where genetics work favorably. We can't cheat biology any more than we can cheat physics. The genetic requirements for viable interstellar colonization, combined with all the other barriers previously discussed, form an interlocking web of impossibilities that reinforce each other. Even if we solve propulsion, the crew would die from radiation. Even if we shield against radiation, the electronics fail. Even if we harden the electronics, the population collapses genetically. Even if we send enough people to avoid genetic collapse, we can't accelerate the massive ship. Every solution to one problem makes another problem worse, until the entire concept dissolves into impossibility. The resource depletion trap. An interstellar spacecraft represents a closed ecological and industrial system, a completely self-contained environment where nothing enters, and ideally nothing leaves except waste, heat, and communication signals. Unlike Earth, where natural cycles replenish water, air, and nutrients through vast planetary processes. A spacecraft must artificially maintain these cycles with perfect or near-perfect efficiency. But the laws of thermodynamics guarantee that no recycling system achieves 100% efficiency. Every process loses something: atoms trapped in non-recyclable compounds, molecules vented accidentally, materials degraded beyond recovery. Over the decades or centuries required for interstellar transit, these small losses compound relentlessly until critical shortages threaten the mission. Consider water, fundamental to human survival and agricultural production. The human body requires roughly 2.5 liters daily for drinking, plus additional water for food preparation, hygiene, and sanitation. A crew of 1,000 people needs 2,500 liters, 2.5 metric tons of water daily, or about 900 tons annually. Agriculture demands far more. Growing food for 1,000 people requires irrigating crops, with water loss through evapotranspiration, the process where plants release water vapor through their leaves. Even in closed greenhouses with humidity recovery systems, some moisture escapes or becomes bound in plant tissues. Estimates suggest agricultural water needs might equal or exceed direct human consumption, doubling total requirements to 1,800 tons annually. Modern recycling systems, like those aboard the International Space Station, recover approximately 93% of water from all sources: urine, perspiration, respiration, and hygiene water. This sounds impressive until you calculate long-term losses. Losing 7% of 1,800 tons annually means 126 tons of water lost per year, water that must either be replaced from reserves or accepted as permanent depletion. Over a 100-year journey, cumulative losses reach 12,600 tons. Over 1,000 years, losses exceed 126,000 tons. Even starting with generous reserves, the water supply gradually dwindles toward crisis levels. Improving recycling efficiency helps, but perfection remains impossible. Thermodynamics dictates that separation processes extracting pure water from contaminated sources require energy input and generate entropy. Achieving 99% recovery still means 1% loss, reducing but not eliminating the depletion problem. And as recycling approaches theoretical limits, energy costs increase exponentially. Removing that last 1% of contamination requires far more energy than removing the first 50%. Energy, as discussed previously, is itself constrained on interstellar missions, creating a vicious cycle where improving recycling efficiency demands energy that isn't available. Oxygen faces similar challenges. Humans consume oxygen through respiration, converting it to carbon dioxide. Plants theoretically reverse this through photosynthesis, but the cycle isn't perfectly closed. Some oxygen gets incorporated into organic compounds that decompose slowly or incompletely. Oxygen also reacts with materials. Metals oxidize, plastics slowly degrade, releasing bound oxygen in unusable forms. Spacecraft air leaks, despite the best seals, represent another loss pathway. The ISS loses approximately 2.2 kilograms of air daily through microleaks, tiny gaps in seals, valves, and joints. For a much larger interstellar vessel, scaling up proportionally, air loss could reach tons annually. This oxygen must be replaced from reserves or regenerated through electrolysis of water, which depletes water supplies. Carbon presents a more complex problem. All organic matter, human tissues, food crops, structural materials derived from plants, waste products contains carbon. This carbon cycles through the closed ecosystem. Crops absorb atmospheric CO2, humans eat crops and exhale CO2. Decomposers break down organic waste and release CO2, completing the loop. But carbon gets sequestered in long-lived structures: wood used in construction, fibers in clothing and fabrics, polymers in equipment, removing it from the active cycle. When these materials eventually degrade, the carbon might be trapped in forms not readily recyclable. Activated charcoal filters, used to purify air and water, accumulate carbon-based contaminants that can't be easily regenerated. Each filter replacement removes carbon from circulation. Over centuries, total mobile carbon declines, while sequestered carbon increases, potentially starving agricultural production. Trace elements and minerals critical for nutrition face especially severe depletion risks. Humans require dozens of trace minerals: iron, zinc, magnesium, potassium, phosphorus, calcium, and others obtained through diet. Plants extract these from soil or nutrient solutions, humans absorb them from food, and waste recycling must recover them for return to agriculture. But recovery is never complete. Trace minerals bind into complex organic molecules during metabolism, some of which resist decomposition. They accumulate in non-recyclable waste streams or become chemically bound in ways that make extraction energy prohibitive. Phosphorus, essential for DNA and ATP, is particularly concerning because phosphorus supplies on Earth are finite and no substitutes exist. A spacecraft carries a fixed phosphorus inventory, and any phosphorus lost to irrecoverable waste or slow accumulation in structural biofilms represents permanent depletion. Structural materials also deplete over time through wear and damage. Metals corrode slowly even in controlled atmospheres due to trace contaminants and chemical reactions. Polymers degrade under ultraviolet light from artificial sources, heat, and mechanical stress. Composite materials delaminate. Fabrics wear thin. Each damaged component must be replaced, requiring raw materials from onboard reserves. The spacecraft must carry enough feedstock to manufacture replacement parts for centuries or accept gradual degradation and eventual systems failure. Even information represents a depletable resource in a sense. Data storage media degrade. Magnetic hard drives experience a bit of rot. Solid-state memory has limited write cycles. Optical media deteriorate. Over centuries, stored information engineering schematics, scientific knowledge, cultural records could be lost unless continuously copied to fresh media. But manufacturing fresh storage media consumes resources. A multi-generational crew might lose critical technical knowledge if storage fails and no one remembers how systems work, leading to irreversible technological regression even if physical resources remain. The fundamental problem is thermodynamic. Maintaining order in a closed system requires continuous energy input to fight entropy. Perfect recycling, returning every atom to its original state and location in the cycle, would require infinite energy. Real systems, limited by available power, achieve only partial recycling. Entropy increases, organization degrades, and useful resources gradually transform into useless waste heat and disordered molecules. Over the timescales required for interstellar travel, this entropic degradation becomes insurmountable. The spacecraft and crew face a slow-motion resource crisis, losing the battle against thermodynamics one atom at a time until something critical fails.